All right, okay, so can we continue? We still have some materials to go over. All right, okay, so I try to change the gear from a direct ammonia synthesis to a plasma-assisted nitric oxide. And in combustion, nitric oxide become a problematic for pollutions. But in a fertilizer, if you can make a NO from nitrogen and oxygen efficiently, you can also make a fertilizer and making ammonia. So therefore, in ammonia, you can make it directly to ammonia in this way through that the Haber-Bosch process. And you can also make another way that oxidize, making nitric oxide. So once you form a nitric oxide, and you can make a nitric acid, you can make other things from nitric acid, you can also make an ammonia process. So which way is more efficient? Today, this way is efficient, and tomorrow, maybe this way is more economically viable. And if a new process is invented. So this is a diagram and presented by Kim. Again, they're showing that a nitrogen reaction with O form NO. This is one of the rate limiting reactions of a zero-density mechanism in thermal NOx formation. So if you're looking at the vibrational state about that nitrogen, you can see that the vibrational state that of 12 is about 110 kilojoule per mole. But even at the, for example, is 5 is 140 kilojoule per mole. So you can dramatically enhance this reaction rate by vibrationally excited that a nitrogen. So, and also, as I said, it's much easier to vibrationally excite a nitrogen than electronically dissociate it. So classically, you have the reaction model by doing this. This is the rate limiting reactions. And then you can, today, maybe you can do it plasma assisted, that using vibrational state and to reduce activation energy and to form a NO. As I said, classically, if you want to do this, that you can only create about 7% around 2000 C. And here, you probably can create that higher than 7% at a lower temperature. That is the hope. So people, and in recent years, people try to pursue this career. They're using this dielectric barrier discharge. But I don't think direct barrier discharge is really a good way to go, because typically that your electron number density is very low, and the temperature is very low. So therefore, the NO formation, you can see, is very low. It's like 1,000 ppm. That far from that the 8% about that the goal you want to do. And then people try to use in spark discharge, because spark, as I know, we talked about this, spark is equilibrium plasma. And they have a high temperature and gas temperature, and the electron temperature is lower. That promote vibrational excitation. Here, you promote the vibrational electronic excitation. Here is vibrational excitation. Here, you look at energy cost of the plasma frequency. They say about 20 megajoule per mole. And then the NO formation is increased to 1,000 ppm, a factor of 4. So then the question is really today in this field that the spark plasma provide a better environment for NOx. And it is also can be optimized for N2 vibrational excitation. And then the yield that what he proposed is that right now it's reaching 3.9%. The energy cost is this. And if you can double this to make it 8%, and then you become the champion. And this is Dr. Kim. I just met him in January in Japan. And he said, our time is coming to doing this. I'm pretty much excited by his work. It's 3.9% already, but it's not, we can easily do it by thermal, produce 6%. But there is an opportunity to optimize plasma. Maybe we can double this or triple this. So I'm trying to thinking, what is the idea I can design a better plasma than this? This is just like the electrode. Many of the nitrogen, they are not really activated because the plasma channel is really, really skinny. Most of the nitrogen are not activated and still rely on the thermal. So this is the problem they have. So I talked a lot about the chemical synthesis. And now I try to doing something, not chemicals, maybe materials. I try to convince you that the plasma can do something far beyond that just chemicals. One of the reasons is that in silicon chip, right, is primarily dictated by plasma. So I try to show you something beyond chemicals and silicon. So here that the plasma instability is very difficult because at atmospheric pressure, you want to create a plasma, the plasma always contracts into a thin arc. You really cannot do much things. The question that by understanding the plasma physics and instability, can we design a novel plasma that is volumetric and high temperature? If we can do that, they allow us to open a door to make a higher concentration of NO from nitrogen, and also open a door to make novel materials that cannot be met at a lower temperature. So if you're looking at that a plasma, if you have a tip, let's say this tip is made by carbon. It's easily you make a carbon tip, like a human hair. A hair is about 10 microns. If you put a charge on the surface, and that electric field generated by the potential is inverse proportional to that R square. If the R is 10 micron, very small, this potential is very, very strong. It generates breakdown very easily. So, but we want to create something uniform. But remember that the charge will be shielded by a Debye lens, okay? And after the Debye lens, everything will be moved, the charge moved by itself, the equilibrate. Then you form an arc. That's really annoying. So can we create an electrode size that comparable to that Debye lens so that not easily for them to contract to create a plasma? So here is a design, and we design a electrode materials. Now it's not a metal anymore. We tried using electrode materials using these carbon fibers and with a diameter around 10 microns and then separation distance around 10 microns. So that's comparable to the Debye lens we want. And so now what happens? Okay, you can see you apply a voltage between these two electrodes, and you have a voltage. Initially, you have a voltage is increasing. The current is really small. And suddenly, you increase the voltage, the current becomes 0. And after that, suddenly there's a tungsten process start to break down. And then contraction become a plasma, and the plasma becomes like this. This plasma is very uniform and stabilized between the two electrodes. And if you reduce the current, even the current and the voltage is about 15 volts, and the plasma is still stabilized there, very uniform. What does it mean? It means that we create a new plasma that can uniform with a larger volume. And what it can do? Well, they can do this. I show you a material that we can do. And he's a materials person. And he tells me that we can, this is at the melting point of materials. And this is a different materials, carbide, nitride, and boron. He said one of the target is the hafnium carbon nitride. That people compute this structure and using quantum chemistry, and they say that this is at the highest melting point materials. But people can make it using spark, then make it in nanoparticles, but no one can make it in bulk. If we have a plasma like this bulk plasma, we can make a materials, bulk materials. So everybody heard that the SpaceX, when they launched their space shuttle coming back, the wing is melting by plasma, right? So if we can coat this wing by these materials, you are never afraid that you are going to melt because they tolerate a 4,000 above. It's much higher than carbon temperature. So this is the materials we made by using this plasma process. And so I try to highlight that the innovation you can do if you understand the plasma physics, and then you can make materials that with highest melting temperature. And the next thing that I try to show you that a few years that we want to say, if you have a battery, the used battery materials, they are typically that is the metal fluoride formed in the surface because fluorine always exists in the electrolyte. The aged batteries on the surface, they form a lot of metal fluoride. So if we want to recycle this battery and the electrode materials, fluorine is very strong. And then it's very difficult to do so. So you have to break down this electrode materials and dissolve in sulfur acid, and then we break down all these ceramic materials into atoms, and then re-precipitate using sodium hydroxide, and then recycle that materials. So we thought that how can we, using plasma, that can generate a very reactive species like O-D that can reduce the materials into metal oxide. So that we don't have to break down that electrode materials into atoms. We just keep the same ceramic structure, but remove the fluorine and the carbon and many things, and then regenerate it. So this is that my postdoc and Chao and my postdoc and Xiaofang, and they created this company. And Bruce is my collaborator at Princeton. And this, what they did, that they did this kind of XRD measurement about that how much that the fluorine can be removed and regenerate a beautiful XRD signal. And this is a comparison about the battery voltage as a cycling. You can see aged batteries is got lithium cobalt oxide, LCO, lithium cobalt oxide, which is typically used in your iPhone. And then you can age batteries, you can discharge it, and then they can see that the charge capacity is 100, 110, 120. The new ones should be 150 and 160. And this is the new materials. This is that they regenerated using plasma. You can see that the performance of capacity and charging, they are almost identical in terms of recycling. I put the 50 cycle, almost identical as the new ones. So this, again, I'm going to show you that using a non-equilibrium process, you can do something you cannot done before and create a new technology, hopefully can make a battery recycling better than before. And the Department of Energy really like it, saying that this is US-made technology, and then they funded our research project, and then right now they got attractive investment from Honda and from a Taiwan company. So what I try to say that, I try to give you an example, I can give you more, but I try to say that in non-equilibrium process, including plasma, could be a game changer for novel combustion engines, ammonia combustion, and it could be a chemical synthesis with a lower carbon footprint, and can making a novel materials synthesis or recycling, and it could be making a biomedicine and silicon chips. So what we really need in the future, not only try to understand the science about the plasma physics and chemistry, but also that how do we control the plasma that is vibrational excitation, electron energy distribution, particularly plasma instability at high pressure. So we need to understand this, how do we selectively excite a state of molecules, and how do we create active species and radicals that we want for synthesis of materials and chemicals. how do we create a lower cost, a lower electronic noise, and the plasma resources, because it prevents us to do diagnostics, particularly for this kind of nanosecond and radio frequency, they create electromagnetic noises. So fundamental understanding is really needed in plasma-assisted chemical manufacturing and combustion. In situ diagnostics of plasma properties of electric field, electron number density, excitation state, and non-equilibrium, and with a time-accurate method and multi-dimension. Right now, that electric field we only can measure is 0 dimension, right? So can we measure it 1 dimension, because the cathode areas and the anode areas, the electric field is much stronger than the bulk areas. So I think that this method is still lacking. How do we measure electric field using second harmonic that can measure one-dimensional? Plasma physics. What is the energy transfer process between excited states, and how does that affect the plasma instability? So that is still a lack of understanding between energy transfers of excited states. Plasma chemistry. Reactions involving this kind of excited state, and then particularly reactions with reaction radicals. For example, a O2 singlet react with alkyl radicals. O singlet D react with large alcohols. There's so many things, reaction rate, we don't even know, and people just guessing it, and far behind about the combustion research. Kinetic models and validated kinetic models. So cross-section areas for large fuel molecules, oxygenated fuels, they are still missing. Multi-scale modeling tools from atomic scale to macro scale. So that is really needed in terms of these areas. What is that? Research questions that how does a catalysis affect plasma? And how does plasma affect catalysis? And both ways, we need to understand that. And then also that, so the plasma effect of catalysis, as I said, when you say thermal catalysis, we basically assume the ruthenium and that the nickel, this remain at catalysis. But in the plasma, this catalysis, there may not be that the catalysis we called catalysis before. They also probably already been hydrided and nitrided and through a plasma mechanism. So how does the plasma also change the morphology of the surface? And how do we make a novel plasma catalysis that is different from thermal catalysis? Anyway, so that is something people want to do. So a lot of things for computation. We really need to leverage that the knowledge in quantum chemistry, and we really wanted to innovate that the molecular dynamic simulation, reaction SF, the potential energy surface is really not accurate. How can we using AIs to learn, machine learning to learn that the energy potential that can do better not only in the gas phase, but also in heterogeneous in surface. How can we do understanding that the energy distribution functions, and particularly at the a highly non-equilibrium regimes? How do we develop a novel catalysis, make a plasma manufacturing, plasma modeling and multi-scale? So all the way from electronic structure to atomic, micro, and macro scales. So there's a lot of things to do, and if you are trained in combustion area, and this all sounds familiar to you, and so therefore you can make a great contribution to this society. So I have a few minutes, and let me try to start to talk about this plasma modeling. So plasma modeling right now is really a new research areas that because we can model something in a quantum chemistry level, but we can model something in continuum regime. But the plasma, that is the length scales, as you know, is just like a one mean free path, right? One mean free path. So really that involving a multi-scale process. And also that the plasma chemistry is so complicated and that many of the rate constants are unknown. So really, how do we develop this multi-scale plasma involving heterogeneous surface is really a big challenge. So there's many ways to do that the multi-scale plasma modeling. So you can do zero-dimensional, and you can do atomic scale modeling. And how do we couple this zero-dimensional model with this surface interaction? You can do microscale, microcanonic simulation, doing, for example, particle in cell. You can do Monte Carlo simulation. And how do you couple the electric field and electrons into it? And that's a very challenging issue. So far, there's no good method in this kind of quantum chemistry prediction, and including electrons and charges to get a surface reaction. So, and many of the plasma catalysis involving packed bed or fluidized bed. So they are highly three-dimensional, time-dependent macro-scale method. So that we really need to understand all this kind of micro-canonic process, and also that how to coupling about the plasma with flow. So integrated model with a plasma catalysis. One of the leading person in this area is Annemie Burgers in Belgium, and she was an expert in chemistry and doing fluid model in terms of plasma. But now she started working on this microkinetic model, atomic scale, and getting into this area. So plasma process, and they have a lot of process, electron interaction with molecules. You got electronic excitation, vibrational, dissociation, excitation, and ionization process, and ionization, dissociation, and attachment. All of them, they are very complicated, and they have different cross-section areas and the reaction rate. The reaction probably is order of magnitude more than combustion we are studying. When we say combustion has a lot of reactions, and this one probably 10 times higher. And this gives a lot of complexity and opportunities as well. So plasma, you can see, as I said in previous thing, you see that the electron energy transfer from electrons to particles, they have a lot of vibrational excitation, rotational excitation, dissociation, electronic excitation. They all depend on electron energy. So you have also that's highly dependent on the mixture. What kind of mixture you have, what kind of electron energy you have. So your chemistry is completely different. So let me show you a few examples that what we have, what we don't have. So the cross-section areas, which is required to calculate that the reaction rates about the plasma reactions. What we have is we have the nitrogen, hydrogen, CO2. If people want to do a ammonia synthesis, CO2 reduction, fortunately, all this rate we probably have, and small hydrocarbons. But for oxygenated fuels, we really have very little. And for large hydrocarbons, we completely is missing. So that is some areas we really need to understand. How do we know that the reaction cross-section and reaction rate in oxygenated fuels and in large hydrocarbons, which particularly that people are interested in propulsion, in engine process. I'll try to show you one example how to calculate that reaction rate. So let's assume that the electrons with a molecular, they form electronically excited and electrons. So first you need to see example, for example, electron collided with nitrogen, they form electronically excited states. And with oxygen, they form this A singular delta and A singular sigma and O higher state. So you typically want to see that this kind of energy of this excited state, they have very high electron energy. For example, nitrogen ABC, they have more than 5 electron volts. That's 50,000, 60,000 kelvins. They are very energetic. And you can have a singlet oxygen, they only have 1 eV, and they're perfect to to coupling with combustion process. So what people did, they're using this kind of rate reaction constant. They need a cross-section area, they need a distribution function with the energy, and then they create the reaction rate. The distribution function typically is fine, and people calculate it, and using quantum chemistry, you can find that the database of different reactions. For example, a O2 singlet, nitrogen electronic excited, A state, B state, and they can find this ARX cat net. And if you do a plasma reaction, if you don't know the reaction rate, this is somewhere the reaction a cross-section area. Once you have the reaction cross-section area, then you need to calculate that the electron energy distribution. That can be solved by using Boltzmann equations. And once you have the Boltzmann equation, you know the electron energy distribution function, and then you put this cross-section area into this equation. You can calculate the reaction rate. And then you plug in to that the chemical solver, you can solve that the reaction plasma. So I probably, due to the time constraint, I probably will not talking one by one. So this one will basically electron dissociation reactions. Again, that you have this cross-section area, here. And you can plug it in. You can see that the electron impact with the methane, they create an oxygen. They have very different channels. Again, in combustion, we say combustion kinetics. Number one important is chain branching reaction. Number two important is a branching ratio of reactions. If you get it wrong, then the model is completely wrong. So here that you can see the electron impact reactions have many, many channels. We have to make sure that each channel, they have the right reaction rate to predict that plasmas. And this is a ionization process. You can do the same thing as we do, and then you have the cross-section areas. So I try to fly by this. Attachment, vibration. So vibration is a very important thing. Electron impact vibrational process. And the question is that how does that vibrational process that affect your reaction rate? So if you look at the vibration of CO2, there are so many levels. And the higher levels actually is very important, particularly that they create electron energy above 1.5 eV, for example, 1 eV. That starts going to coupling with your low temperature chemistry that start to dissociate and molecules if you have a vibration level of 5. So, and to calculate that reaction rate, we have, say, electronic excitation, vibrational excitation, and that vibration will be relaxed. This is called VT, vibrational translational relaxation, and make it hot. A VV relaxation is a one molecular vibration that transfer to another molecular with a higher vibration. So there's a VV relaxation. And then you have a chemical reaction with vibrational state. All these things needs to be properly considered in the reaction mechanism. For example, one of the big flaws in that the plasma kinetics involving vibration. You have a vibrational molecules involved here, and you calculate the reaction rate. Basically, they're using a correction. For example, the original activation energy is delta E, and then with a vibrational molecules, you put a vibrational energy here, you plus a alpha. And that alpha is basically calculating the ratio about the forward activation energy EA is here, and the backward reaction about EA2 is here. So this is a very rough ideas, but unfortunately that in plasma chemistry, physics areas, a lot of people are using. Today that with this is a DFT, quantum chemistry calculations, you can actually predict what is the reaction rate. I hopefully that one of you in this audience in the future can come up with a database that what is that the reaction rate involving electric field, vibrational excitation that help us to improve the accuracy of vibrational excited molecules in the reactions. Okay, this is vibration. So let me talk about that the challenge about modeling. So there are all these things of a plasma modeling. You have a multiphysics, you have photons, electrons, electronically, vibrationally excited states, At the same time, that in plasma, you generate electromagnetic wave, field, acoustic waves, shock waves, ignition, and combustion. They are very multi-length scale, multi-time scale, multi-species, and a lot of stiffness. How do you integrate the equations? But fortunately, that there are softwares being developed. If you are only interested in 0D, and there's a software called ZD Pluskin. What the ZD Pluskin does is that they involve this Bosque solver. The Bosque solver is trying to solve this Boltzmann equations about electron energy distribution. So plug in this Bosque solver and with a ordinary differential equations, and then they can integrate the species and in a ZD Pluskin, so that with the approximate assumption about this first order about the Boltzmann equations, this Boltzmann equation solver, which only consider in that a velocity, a direction projection with the theta, only one direction. So that can solve this. This give you a zero-dimensional understanding what is plasma chemistry. So you need two things, that Bosec for Boltzmann solver, you need the ZD Pluskin to integrate that your ODE solvers for. So that's very convenient. You can download it and for free, and then you can see that the Bosec solver you can download from this slide. And so you can coupling this ZD Pluskin with chemicane. So today we have a chemicane, and that can handle combustion chemistry. You can have a ZD Pluskin that can handle that plasma chemistry. So you can couple them together and do that the plasma-assisted combustion, which probably only take you probably a few months to do so. And it's not that difficult. First of all, you solve that the plasma equations, and you solve that the chemical equations, and then you splitting that the reaction. You basically do a combustion process, you do a plasma process, you combustion, plasma, combustion, and plasma. You just split that time step into half and half. If you want to look at we have a paper published in this area. It's very robust, and then so this allows us to do this kind of modeling. For example, if you have a nanosecond plasma and you have a DC plasma, this is called hybrid plasma. You're using that the nanosecond plasma to drive electron impact, electronic excitation. You're using DC plasma to drive vibrational excitation, so that you can understand how this hybrid process, you can enhance that the combustion process. So here is that they show you example that the kinetic model, you can using hydrogen, you can using nanosecond discharge with a low pressure or high pressure with a different kind of pressure. So they can give you electron number density as a function of time with a different hybrid. For example, DC is 1,000, 10,000. So what you are interested to see, you can see that this is a more fraction of methane and oxygen vibrational state. You can see that the DC current, and that is that the O2 vibration is dependent on how much that the DC current, the electric field. So this basically shows you clearly that you can using that the hybrid plasma, a nanosecond with the DC. You can control the vibrational state of methane and control the vibrational state of oxygen and O2 singlet production, depending on what you want. So this gives you a new knob. You can tune the plasma chemistry using this hybrid plasma discharge. So you can simulate that ignition process. They can identify you which reaction is important to give you that the radicals. What do you found that the Townsend about the 20 Townsend about the DC that give you that the fast ignition process. So this kind of thing using again question. Yeah, let's do it this way, okay. Electron impact process, because you need cross-sections. Ion impact process, you need cross-sections. That cross-section is integrated in ZD Pluskin. And in combustion production, they don't have it. you have to supply your own chemical solver to calculate the reaction rate by yourself. So that's why you need two partners. But this gives you a wonderful flexibility. You can change the chemistry whatever you want for ammonia combustion, for hydrogen combustion, very friendly because you are expert in chemical. And then you only need to change that to the plasma part if you change the reactant, right? Is that clear? All right, great. And then, so we can do this a one-dimensional plasma modeling and to solve this, for example, the Poisson equation. This is the electrons and the ions and fluid equations, compressible flow. You can solve understanding how that the number densities as a function of time with a different states. So that really give you just like a chemical now, it gives you good understanding. Today in plasma combustion or plasma chemical reforming, doing this kind of zero-dimensional, one-dimensional, I think that right now is just like very trivial now because of the effort we have done in the last few years. So you can also, this is a effort in Anna in France. He developed a two-dimensional fluid solver to solve the fluid mechanics. And this is the plasma drift and diffusion, Poisson equation, electrical field, and he solved this two-dimensional discharge in anode in plasma physics. So that's what he shows, that if you have a nanosecond plasma discharge, this is a cathode, this is an anode, this is a cathode. You can see the ionization wave, the streamers from, this is a negative streamer, this is a positive streamer. You can see the negative streamer develop very fast compared to when they merge, and the electrical field disappeared because the device shifts, right? So they can calculate that the time histories of different species involving this kind of reactions. They can identify what are the key reactions in the gas phase and in two-dimensional simulation process. So today, that is state of the art plasma modeling. It can give you a detailed chemistry in probably two-dimensional and even three-dimensional modeling, just like a combustion we are doing. But it's very slow, only a very fast process, nanosecond, because the time step is very small. And a few years ago, that a group of people and in France, and they developed this they call Pascal code for nanosecond surface DBZ discharge. And this Pascal code gives you a mesh generation, solve Poisson equations for voltage, and calculate that the flux of transport ionization, photoionization, and electron impact ionization process. They also have a parallel module for parallel computing. It's really good in the matrix. So I talked to this the author, probably Yifei Zhou, and then I collaborated with him. And this is the typical simulation, what they've done in terms of discharge. You can see that how they discharge from an electrode to form as a function of time, including photoionization. But photoionization is important for what? For what streamer? The negative streamer is basically electron ionization process. That is the positive streamer. Yes, positive, so you need the photoionization. You have to make it appropriate, otherwise you cannot model the speed of ionization. So they did some kind of a modeling to see the current as a function of time. This is a Pascal simulation, this is a benchmark modeling. They agree reasonably well. So that was done probably 2017. Then I just draw my attention. I think that we should collaborate. That is this, we developed this. At Princeton, we developed this ASERF, adaptive simulation of unsteady reactive flow. We have this a compressible flow solver, and with adaptive chemistry, and then this is Pascal. So we put one graduate student and a postdoc to try to couple this together. So our first paper was published in 2021 that we are able to solve for example, ignition and between the two electrodes with the different geometries, with a different electric field and voltage. We try to understand that how that the electric field and that I don't know what it is, so affect the discharge. this gives us a wonderful opportunity to understand how that what reactions is important, what species is generated, what kind of electrogeometry is better for plasma discharge and ignition. So here I try to show you example. This where experiment was done. I go back. So it's done in Air Force Research Laboratory. They're using a high frequency discharge to see how that the ignition occur. Sometimes they say high frequency ignition can happen, low frequency you don't. And this is published in Combustion Flame 2017. But no one can model that. But after that, you see that in 2023, this is our paper, and we can model that the two-dimensional, you can see at a lower frequency ignition will be, you can see again, I don't know how this is. And lower frequency, plasma frequency, because ignition kernel, they don't overlap each other. They don't create a big ignition kernel size. For ignition to happen, you can see the ignition will die. If we have a high frequency, the two ignition kernel, they overlap each other. They can create a volume that is bigger than the critical ignition volume, so that ignition can be successful. And Anime developed a bogus. They developed this microkinetic a model to solve that packed bed discharge and to see how that the dielectric barrier discharge to affect that the CO2 reduction to CO and oxygen. So try to show you some of the result. You see how that streamer is developed between the packed particles. And this is that the electric field, and it developed from here and propagate towards that the gas phase. This electron energy is very hard, very high electron energy between that the sharp tip. When they have very sharp tip, the electron energy is very high. And then so they can simulate this, but I don't think that the chemistry of that process is properly modeled yet. But what I try to say that they can solve that the streamer propagation, and we can do it too. But they can do it in a way that using that the particle in cell method. They can solve this the time-dependent development of an electric field, and it's the electron number density, and how that the discharge is happened, and how that the plasma is developed. So what do I try to say that today that a multidimensional plasma-assisted combustion, multidimensional plasma catalysis in a packed bed and catalysis, and now is available, but is not accurate because the reaction rate is not well known, and the chemistry and then plasma surface interaction is not well known. So you can see all this kind of stuff in terms of plasma modeling between a plasma and the catalysis. But really that the chemistry part, as I always said, particularly at the heterogeneous surface and then at the gas phase, that the reaction mechanism is poorly known. And I think that I don't want to occupy a lot of time, and I try to highlight to you what is we know, what we don't know, what we can simulate, what we cannot simulate because of the lack of our knowledge about the plasma chemistry. Physics is important, but I think that the chemistry become more important today. There is a large barrier. So I hope that in this 3 days presentation, I give you that some kind of overview how plasma can enhance combustion, how plasma can control non-equilibrium, then open a new research direction in terms of not only in controlled combustion, but also that in chemical synthesis, material synthesis, and discover some new physics and theories so that you feel interesting about it. And I think that the society give you guys, particularly decarbonization and climate change issues, give you guys a sustainability a wonderful opportunity to pursue this high risk and high payoff research. And I wish you good luck in your research. In the future, if there's anything that we can communicate, collaborate, we can learn each other, we'll be happy to do so. Thank you very much.